90-degree rotation, and it vanishes when this angle is 45 degrees plus the usual multiples. Now, when we analyze this in more detail, we find this Josephson free energy that is only dependent on the relative phase between the two order parameters, and it leads to this landscape with 1 minimum at small twist angles and 2 minima at large twist angles. A phase diagram in twist angle temperature plane looks something like this, where there's a wedge of this topological superconductor, and interestingly, at exactly 45 degrees, this phase extends all the way up to the native critical temperature of the monolayer, which is potentially 90 degrees in BISCO or thereabouts. I also told you that this phase is interesting because it's gapped in the bulk, and it's topological in that it has non-zero Chern number, and this guarantees that you have these unidirectional edge modes that exist, and here they are visualized in the spectral function evaluated at the edge. Okay, so that's a kind of a 2-minute review of what I said yesterday. Here's a question that I've been asked often during this talk. So, you know, is there Majorana fermions in this? It's a topological superconductor. Does it have Majorana fermions? And it's a kind of slightly tricky question, which I will now try to answer. So, indeed, you can view those edge modes as Majorana modes. And that's just a generic statement that basically modes, excitations in a superconductor have this Majorana character. But in the sense that, so the question is, are they useful in any way for quantum computation? That's the motivation that people often take when they discuss Majorana modes, and the answer is no. So the reason is because we start from a spin singlet superconductor, the Chern number always will be even. And so we have Majorana modes, but they always come in pairs, and they are not isolated in space. So we cannot really use them to do any sort of braiding, and we cannot employ their non-abelian exchange statistics that we would like. So as such, this bilayer, the answer is no. We you know, in some sense, there are Majorana modes, but they are not the kind that can be exploited for topological quantum computation. Of course, there's been proposals in the literature, and there's been experiments in other types of systems where you have these Majorana fermions, or there is evidence for them. People still debate how solid that is. So this is Majorana wires, semiconductors proximatized with superconductors. There is some evidence in vortices of iron-based superconductors, and this is still controversial, although, you know, people demonstrated these zero modes, and they have some desirable characteristics. There is these artificially created wires. This is Ali Yazdani's work, these ferromagnetic chains on top of a strongly spin-orbit coupled superconductor. This is perhaps the strongest evidence for Majorana zero modes, because one could go and with STM spatially resolve their position, and indeed they are found at the ends of these artificial wires. So there's many different systems. Each of them you can criticize, you can question, but what I'd like to emphasize is that theory behind this is solid, right? So this is a theory school, this, you know, the theory of Kitaev wire and the Foucault superconductor, where these appear, Majoranas appear in vortices. That's all solid theory based on, you know, well-established BCS theory of superconductivity, and nobody doubts that. Where any sort of doubt exists, you know, is the question whether or not these zero modes are actually corresponding to Majorana fermions or something else. And the problem also is that, you know, the sort of smoking gun experiment, beyond going just beyond looking just at the spectroscopic signatures, would be to demonstrate these non-abelian exchange statistics, which also theoretically is a sound prediction. Nobody doubts that. But this is experimentally very hard to do. And so, for instance, Microsoft is investing untold millions and billions of dollars in producing some structures out of these wires where this braiding could be implemented and tested. And after, you know, I don't know how many years now, it's pushing 10 years. I haven't seen any big announcement. So it's a hard problem, and I think one day it's going to be done, but we're not quite there yet. So with this preamble, there's a question here: can we think of a variant on this twisted bilayer cuprate construction that could host Majorana fermions? And I'm going to give you sort of two ideas along those lines that potentially can be useful. So here's the first one of them. So what's missing in this twisted cuprate bilayer? It's a topological superconductor, but as I mentioned, it's obtained from two ordinary singlet superconductors. So it does not by itself have Majorana fermions. What's missing in that picture is strong spin-orbit coupling. What you need generically to have a Majorana fermion is to build a superconductor on top of something where degeneracy between spin up and spin down is broken. And you can achieve that by either spin polarizing your normal state or by introducing spin-orbit coupling. So here's the first idea, and this follows the well-known work by Liang Fu and Charlie Kane. We're thinking about here a strong three-dimensional topological insulator, and we're thinking of putting this twisted bilayer on top. Those of you familiar with the original Fu-Kane proposal, they do the same thing, except they put on ordinary S-wave superconductor. And what they show by a simple calculation is that at the interface between the S-wave superconductor and the topological insulator, the surface state is transformed into this topological superconductor that hosts Majorana fermions in its singly quantized vortices. So we kind of shamelessly adopt that same strategy and ask the question, does this kind of configuration support Majorana zero modes in their vortices? And the answer to this is yes. I'm not going to go through the calculation. It's relatively straightforward. Here's the Hamiltonian. And it's basically effective Hamiltonian for the surface state of topological insulator, which is a single Dirac fermion that is, in the simplest case, exists at the center of the surface Brillouin zone. And then I just imagine that I proximity couple it to this superconductor, so that's where this gap comes from. And the only difference from the Fu-Kane is that in Fu-Kane solution, this is just a constant independent of momentum because it's an S-wave superconductor. Here we have a d plus ID superconductor, so this has some structure in momentum space. Okay, and I'm not writing here the details because maybe they are not as exciting or interesting. It takes a little bit of doing to solve this equation or to solve this Hamiltonian in the presence of a single vortex, but it leads to just two coupled differential equations like this, and we can solve them. And indeed, they confirm that there will be a single Majorana zero mode in a vortex of that superconductor. So here's the wave function of that Majorana fermion. We show that it's localized, meaning it decays exponentially away from the vortex core. And yeah, I don't have the numerical solution, it shows that it's separated in energy from all the other levels. So this is one possible way how one can leverage this, twisted bilayer to create Majorana fermions. It's a kind of a cheat because I'm not really in any way using the topological nature of this twisted bilayer. I'm simply using it as a superconductor that proximatizes the surface state of a topological insulator. Now, where there could be an advantage is that this is a high temperature superconductor with a large gap, whereas anything else that you might put on top of that is a low temperature superconductor with a small gap. So that's where an advantage might be. Other than that, it's basically a variant of this Foucault construction. It was not a priori obvious that the D plus ID superconductor would do the same as S-wave. I suspected that would be the case, but then the solution confirms that. Now, you may also ask, well, why do I have to bother with twisting anything? Couldn't I just put ordinary cuprate and be done with it? And there the answer is no, because cuprate, when it's untwisted, is a D-wave superconductor. So it has these gapless excitations down to 0 energy. And you don't want that, right? If you want to use Majorana 0 modes for quantum computation, you want to have everything gapped in your system. You don't want to have any low-lying excitations coming from Dirac nodes of a superconductor or anywhere else. So basically here, the twist is used to create a fully gapped superconductor, but its topological nature is not really being used. So this is idea number 1. Here's idea number 2. This is not cuprates anymore, but the philosophy is similar. This goes back to what Jane and some other speakers were talking about. This is now graphene and other dichalcogenides. And in general, the idea is as follows. So there are some materials, two-dimensional materials, like rhombohedral trilayer graphene, Bernal bilayer graphene, and zirconium nitrate chlorine that are thought to be a spin triplet valley singlet superconductors with potentially F-wave order parameter. So let me unpack that for you. All these materials have a hexagonal Brillouin zone, and they have small Fermi surface pockets in the corner of this Brillouin zone. And for RTG and BBG, these variants of graphene, that happens upon suitable gating and displacement field. And I'm not going to go there, but in some part of this phase diagram that Jane was showing us as a function of charge density and displacement field, their normal state looks like this. And importantly, these pockets here are spin polarized. So through interactions, the system just chose to fill only, say, spin up states, and they form this kind of metallic normal state. And then at low temperatures, this goes superconducting, right? So these are experimental facts. And those superconductors break this Pauli limit, sometimes by factors of 10 or so. So they are definitely unconventional. And that led to this idea of spin triplet valley singlet superconductor with F-wave order parameter. Let me emphasize that this is not confirmed. This is just a theoretical idea that sort of fits all those facts. And so why F-wave? Let me answer that. So F-wave is angular momentum 3. So you have S-wave, angular momentum 0, P-wave, D-wave, that's angular momentum 2, and F-wave is the next one, so that's angular momentum 3. Importantly, this is odd under inversion, right? because you have every odd angular momentum is also odd under inversion, P and F. And so that's exactly what you want. You want something odd under inversion if you have only one type of spin, because you cannot create spin singlet. You only have spin triplet that's even under exchange. So in order to satisfy the Fermi statistics, you want something that is odd under spatial inversion, and that's why you need odd angular momentum here. Now, why F? Well, F wave, because it's L equals 3, has precisely the property that fits nicely on this hexagonal Brillouin zone. Basically, what it does is that you simply have an order parameter that is positive here, negative here, positive here, negative here, and so on. Okay, so that's your F wave with this type of Fermi surface. What you see here in the middle, that's a representation of that F wave order parameter. It vanishes along these 3 lines, and it's maximal along these lobes, and always, of course, changes sign upon 30-degree rotation. So, 60-degree rotation. So the conjecture is, again, that these materials have this type of superconducting ground state somewhere in the part of their phase diagram. Now, if you look at a topology of this, even though this is spin triplet F wave, it's topologically trivial. It's fully gapped, but topologically trivial. It's fully gapped because even though this order parameter has nodes, they never intersect these small Fermi surfaces. So that's why it's fully gapped. And initially we thought, could this be topological actually? But if you look into the big table of tenfold way, you find that actually in this class, I forgot which class this is, but this has spinless time reversal symmetry and charge conjugation symmetry. You find that that class is actually empty in 2 dimensions. There's no possibility of topological phases. The only possibility is to break the spinless time reversal symmetry. And that's exactly what this proposal that's been dreamt up by my postdoc Benjamin, that's what it's about. Excuse me. So the idea is to follow the construction in twisted cuprates and form a bilayer of this type of material, again, close to the maximal twist angle, which in this case will be 30 degrees, not 45, but 30, because this is hexagonal Brillouin zone. So let me show you a quick animation how this could work. So I take one layer of this material. I take another layer. Now I rotate it by 30 degrees, and I make it into a bilayer. Okay? Now, notice what's happening here. What's happening here is that the 2 order parameters, which now sort of cover this whole new Fermi surface, are being frustrated, right? Because blue, wherever blue is touching orange, that's where the order parameter is unhappy, because there's positive trying to connect with the negative. Okay? And that already tells you that's somewhat similar to when you have 2 D-wave order parameters with 45-degree twist, there is a similar frustration. So you may ask the question, how is the system going to resolve this frustration? It can resolve it by setting up some nodes to actually change sign, where the order parameter remains real and just goes through 0 to connect between these blue and orange parts. Or it can take advantage of the fact that, in principle, this can be order parameter is a complex quantity, so it can go through imaginary values and form some complex combination of the 2. And that would be an interesting situation. Just like in a case of twisted cuprate, we argued we get a D plus ID. Here we could get F plus IF, and that would actually break the spinless time reversal symmetry of this original system and could potentially be topological. So in this case, Turns out the calculation is quite a bit more complicated than in the case of cuprates, precisely because these small Fermi surfaces are centered at the corners of the Brillouin zone. So one has to do here sort of Bistritzer-McDonald type analysis with superconductivity on top. So one has to really consider properly all the scattering, wave vectors, and so on to solve this problem. Question?
What is different? Even initially we had blue and orange and blue pockets touching in the center of the.
So what is different compared to cuprates is that here the Fermi surface is really very small near the corner of the Brillouin zone. In cuprates, you don't have that. Those Dirac points are not pinned to the corners of the Brillouin zone. Rather, they are inside the Brillouin zone. So in that sense, it is different.
What I meant is, what is different because they were already touching there, and you said the order parameter would be unhappy.
Okay. So here, this is not really physical. What I plot here, or what my postdoc plotted in the center of the Brillouin, so that's not a Fermi surface, right? That's just a representation of the order parameter. Where the electrons reside is on these small corners of the Brillouin zone, and the coloration here is meant to code or encode the sign of the gap on that part of the Fermi surface, right? So you notice that the blue and orange are not really touching or even close to one another. So the order parameter technically goes through 0 at this line, but there's no electrons that are affected by that, right? However, here, these two Fermi surfaces are actually touching, and that's why these electrons have to decide whether to have a positive or negative order parameter. They cannot have both, right? So that's where the frustration comes in. Any other question? Yes?
So in this material, at least in biodiagraphing, you have to apply the in-plane field to induce that kind of spin triplet superconductivity, right?
Only one of them, I think. I forgot which one of these. You get this SC2 even in zero field in one of them. Yeah.
But somehow in the case that if we have to apply such in-plane field, like would it affect like this picture of simple?
We haven't really considered the effect of in-plane field. You could argue that it may be detrimental to this. On the other hand, this is not Pauli limited, right? So in-plane field doesn't kill the superconductivity. Rather, it creates it. So from that standpoint, you may think it will not really disturb this putative F plus IF prime state. Although we haven't modeled that. We just did a zero field calculation, which was complicated enough for my postdoc. Well, it was his idea. I told him this is going to be hard, and he said, OK, I can do this. So yeah. Anyway, so he set up the whole Bistritzer-McDonald calculation with the superconducting order, and here's the result of that calculation. This is the phase diagram. The axes are here, the twist angle, and chemical potential. And there's many different phases, and I will not really describe all of them. So large part of this, away from exact 30 degrees, this orange is nodal F-wave superconductor. So that's when the order parameter decides, or energetic decides that the order parameter just remains real, doesn't break time reversal, and instead has nodes. So that's a gapless superconductor, which is really not interesting for the purposes of having Majorana fermions or anything like that. However, there is an interesting part of the phase diagram, which is this light blue. This light blue, which occurs here and in a fairly large area down here. And this is the chiral F plus IF prime superconductor that occurs in a on a, so to speak, single Fermi surface. So one should think of this as these little Fermi surfaces as coalescing into one large Fermi surface, and on it there is a single F plus IF prime, a superconducting order parameter. Yes?
So in this situation, there is no Moiré physics, right? Because you're twisting at a very large angle. So what do you mean by High-Tccuprates?
Okay. So, yeah. So at exactly 30 degrees, this is a quasi-crystal, right? And also, you cannot really consider, as in Mr. to McDonald, you consider two sort of Dirac points that are close in momentum space. This is just not that situation because they are equally far apart. So there's a method that is inspired by Bistritzer-McDonald model, which allows you to treat this type of quasi-crystalline situation. And it's been developed by this Japanese group of 7 authors that I can't now really recall all their names. And it basically is very similar to Bistritzer-McDonald, but it's more complicated because you literally explicitly putting in all these Dirac points and all their images in reciprocal space. And then you have to impose some cutoff. So in the end, you kind of diagonalizing some gigantic matrix. And that's where you get this phase diagram. Of course, in our case, we're not only interested in the normal state, we're interested in superconducting state. So this was quite a tour de force that Benjamin and helped with my 2 students went through. But I think this is a correct result of that calculation. We ran lots of checks and balances, and it all made sense. So, okay. So to the extent that we can trust this phase diagram, there is a significant part of it where there is this interesting chiral F plus IF prime phase. Did you have a question?
I just want to make sure I understand. For small mu, the pockets, original pockets become very small.
Yes.
I see. So in the limit where the pockets do not touch, you just want to keep the nodes.
Yeah. Okay. So this is the phase that we're after. This is the non-abelian topological phase that we would expect based on general arguments to have Majorana 0 modes, and indeed that's what happens. So so once we kind of focus on this phase, we can construct a toy model of this F plus IF superconductor just to confirm that it has these properties. And indeed, that's what happens. So basically, this is a representation of that toy model. We work on a triangular lattice. And basically, for those of you familiar with models of superconductivity, to model F wave, you need to put your superconducting order parameter on your bonds. And to do this F and F prime, you need to use first and second neighbor bonds on this triangular lattice. And then what you can do, you can put this on a strip, as we did with our cuprate. And this is the spectral function. So in the bulk, this is gapped, as you would expect. And this is the spectral function on the left edge and the right edge. So you can see that there is protected edge modes. But importantly, now you have an odd number. Okay? So instead of 4 in D plus ID, here you only have 3. And 3 is actually as good as 1. So what happens is when you have 3 Majorana modes, 2 of them can hybridize, right, and go to finite energy, but one of them has to stay at 0. So this is exactly what's happening here. So odd number of Majorana modes is good. And just to make completely sure, we've done a simulation for a vortex. So basically, we put this model on a hexagonal domain like this. We put a vortex in the middle. And indeed, what we see is a zero mode. In fact, there's two zero modes. One lives at the center, one lives at the boundary, and you can run various checks to see that they are actually self-conjugate in terms of their wave function, so they are indeed Majorana zero mode. So this is a sort of higher angular momentum analog of a two-dimensional p plus IP superconductor, which potentially could be created by this twist angle engineering. Is it a realistic proposal? Well, you know, you have to ask people like Jane. I don't know. But in principle, at least from this spin singlet valley triplet superconductor that we think exists in these materials, by twist angle engineering, one should be able to get that near 30-degree twist, and by tuning the chemical potential. OK, so this is Majorana idea number 2. My third part is more conventional. So instead of chasing the dream of topological quantum computation, we turn to sort of more conventional qubits. And if you look in the literature over past 10 years, what is the sort of most successful of all the qubit architectures is the transmon. Okay? And transmon is based on a 2002 proposal from a Yale group. And I will describe how transmon works. But let me, on this slide, simply say that all these most successful superconducting quantum computers that are currently in operation are based on transmon qubit architecture. So IBM, you know, you can get an account and you can actually access remotely this IBM Falcon quantum computer. You can perform elementary gates and so on. Similar for the Google quantum computer. There is Rigetti, and there's 2 other companies that have these sort of what they call now NISQ quantum computers, which is noisy intermediate scale quantum computers, and cannot quite do useful things with them yet, but they already do non-trivial things. Okay? So the question was this: can we somehow improve the transmon qubit based on these ideas of twisted cuprates and so on? So here's an idea, but before I talk about the actual idea, let me remind you how a conventional transmon works. And this is the original paper. Sorry, I thought I said 2002. It's 2007. This is an extremely influential paper where, for the first time, they proposed this design. So this is a circuit diagram of transmon qubit. And it looks kind of complicated, but the important part is this. So it's basically a couple of Josephson junctions connected in parallel with a capacitor. Okay, that's what it is. And the rest of what you see here is just a control circuitry. This circuitry is used to address the qubit and read it out. And you know, we may not really worry about it for now. So the heart of the qubit is, again, a pair of Josephson junctions and a capacitor. And here's actual realization of that transmon qubit. These blue areas, those are aluminum, which is the superconductor. And the qubit actually is this little thing down in the middle that you can barely see. Those are the 2 Josephson junctions. And this comb here, that's the capacitor, basically. It's nicely color-coded. Dark blue corresponds to the upper plate of the capacitor, light blue to the lower plate of the capacitor. And the whole thing is in the microwave transmission line. And that's how you manipulate this qubit. You send microwave pulses, and they correspond to, that's how you can operate it, basically, make transitions between its states. OK, so that's a qubit. That's a transmon qubit. here's the mathematics behind it. So this is the so-called transmon Schrödinger equation. And let me unpack that for you. First of all, this is the wave function, psi. Phi is the phase across the Josephson junction. Now, for simplicity, this transmon equation just considers you have one Josephson junction. I will explain why in practice you want two, but let's simplify even more. Let's just consider just one Josephson junction in parallel with a capacitor. Okay, so that Josephson junction has some phase across it, and it's in quantum regime, so the phase is allowed to fluctuate, and that's why you have a wave function psi that describes the probability that the phase value is whatever it is. Okay, so Ej is the Josephson energy. Cosine phi is just that cosine potential, which classically has a minimum at 0 because there's a minus sign here. So that's the energy of the Josephson junction. This first term here is the charging energy of the capacitor. Ec is the charging energy, where the capacitance is at the bottom, E squared is at the top. D over d phi is basically the number operator, canonically conjugate to this phase. As you know, in superconductivity, Cooper pair number and the phase are dual in the sense that like momentum and position in quantum mechanics. And the Schrödinger equation basically looks like so. The important thing is this Ng, which is the offset charge. And this is basically, once you go down to quantum level, when you consider charges on this capacitor that are comparable to single electron charge, you have to worry about the charge distribution on capacitor plates, which can give rise to some arbitrary offset here. And where exactly that comes from microscopically, there's chapters in books on quantum computation which analyze where exactly this comes from. But the fact is, and this is deduced empirically by studying the frequency response of a quantum capacitor, there's always this offset charge, which is basically difficult to control, and it also fluctuates slowly in time. And what determines those fluctuations, again, there's chapters in books that discuss that, and it's still to some extent unsettled. But it's just a fact that you just, when you want to design a practical qubit, you cannot neglect this. So you have to put this offset charge in. And the Transmon paper actually solved the problem of this offset charge. And let me, on the next transparency, tell you how they did it. So it's just the fact that the qubit of this type is described by this equation, and there's this essentially uncontrolled variable which slowly fluctuates in time. Okay, so here's a key figure from that Transmon paper back from 2007. When you solve this equation, it's a relatively easy matter. It's a single particle quantum problem with a cosine phi potential. So you can numerically or even analytically diagonalize it. The solution is so-called Mathieu functions, which you can find in the books on mathematical physics. And what you can do, you can now plot the energy levels of this Schrödinger equation as a function of this offset charge Ng. Okay? And there's two parameters in this equation, the charging energy and the Josephson energy. And how this spectrum looks like depends on the ratio of those two, as you might expect. So the early or the predecessor of Transmon qubit was the so-called Cooper pair box qubit. And that operated in the regime where Ej and Ec were comparable, so roughly this diagram. And you can see why this Ng was a problem. The energy levels of that qubit depend quite strongly on this offset charge, right? You see a strong dependence here. And if you want to use the two lowest levels of this qubit as your working logical states, then this is a problem, because imagine during the operation of your qubit, this ng just fluctuates, right? So the frequency of your qubit just keeps changing, and that leads to problems with decoherence. That leads to problem with how you address that qubit when you don't know what the frequency is at any given time. So that was a problem with the Cooper pair box. And kind of interestingly, this paper was first to actually point to that problem. That, this is the problem, and they also pointed a way how to solve it. And the way is quite ingenious. So just basically go to the limit where the Josephson energy dominates. So you can see how when you increase this this ratio EJ over EC, the dependence on this uncontrolled offset charge just is getting weaker and weaker, right? When you go to what now is called the transmon limit, where this ratio is on the order of 50 or more, you can see that the energy levels are basically flat. So these are flat bands, but in a different context. And now this can be a useful qubit, because even though your Ng is fluctuating, the energy difference between your two lowest levels is constant, doesn't depend on it to leading order at least. Okay, and so that was the revolution in 2007, which allowed all these quantum computers to be eventually built. They are built on this principle. Now, what's the drawback of this? Why we're not completely happy with that? So the drawback of this design is that the spectrum in this transmon limit becomes nearly harmonic. What do I mean by that? Notice that the difference between the level 0 and 1 is almost the same as the difference to the next level. So that's like a harmonic oscillator where they would be exactly the same. And why is that a problem? Well, that's a problem because the way you operate this qubit when these two lowest levels are your logical 0 and 1 is by hitting it with microwave pulses, right? So for instance, you want to excite from 0 to 1, you hit it with a microwave pulse that has this frequency. However, you cannot ensure if the energy difference to the third level is the same. You cannot ensure that you want, with some probability, excite your qubit into the third level, right? Or, in this plot, there is a small difference between those two. In order to prevent excitation to higher level, what you need to do, you have to tune your frequency very finely to exactly this frequency. And what that means is that in time domain, this has to be a long pulse, right? Because if you try to send in short pulse, that will be a superposition of a lot of frequencies. And with some probability, then you will end up in this unphysical, or well, it's a physical level, but it's outside of your code space. So basically, when you have 50 qubits and just one of them is excited into this third level, you're done with your calculation because you're kind of out of your logical code space. And unless you can somehow mitigate against that, you basically have to repeat it from the beginning. So weak unharmonicity is a kind of a primary bottleneck which can be dealt with, but it limits the speed with which you can operate these modern transmon qubits. OK, so here's the summary. I guess that's what I just said. This disadvantage is this weak unharmonicity. And it limits the maximum speed of operation because you have to address this with a very precisely tuned pulses in the frequency space. OK, so how does, or what can we do about that? Can we do about something about this based on these ideas on twisted D-wave superconductors? And here's the proposal for a transmon with strong unharmonicity, which we call the D-mon. A kind of funny story we submitted this paper with a daemon in the title to the archive. And for the first time in my life, I wake up the next morning and there's no paper on the archive, even though I submitted it myself the day before. And I'm like, what's happening? And I get this nondescript email from the archive saying that our paper has been put on hold pending further administrative processing. And I was puzzled by that, but then, I think demon in the title did it. So we don't know that, but I think archive is doing lots of sifting because you don't want crazy people posting their things on the archive. And when there is a demon in the title, I think that raises flags. So it took about a week before it actually got appeared. And I guess what happens is that AI first filters it, and then it has to go to actual person who looked at it and maybe decided that we're not crazy, and then it went. So anyway, so daemon. The basic qubit design that we're proposing is quite simple. So we have a D-wave superconductor on top of an S-wave substrate. So this is a flake of a cuprate, just few monolayers thin. And this could be any S-wave superconductor in principle, but there's some material constraints that I can discuss if anybody asks me. So what is the free energy of this? Similar to our analysis with D-wave, I have these terms. However, if both of these materials respect C4 rotation symmetry, as cuprates do, and if we put in a S-wave superconductor that is tetragonal, then this would be the case. We can conclude that, again, this B term has to vanish. And this is because under C4, the S-wave order parameter is invariant under C4 rotation, whereas D-wave order parameter goes to minus itself. So this term is just not an invariant, right? It would map to minus itself, so it has to vanish. If C4 symmetry is weakly broken, as happens, for instance, in BISCO, then we would conclude that this term is allowed, but probably is very small because it's a very weak breaking of C4 symmetry in a crystal like BISCO. So I will continue with the assumption that this B is 0, but then I will bring it back later on to see what the effects are. So the Josephson free energy here looks like this. There's just cosine 2 phi term. As opposed to cosine phi, that would be the conventional Josephson free energy. So the transmon, imagine we make this into a transmon now. We couple it to a capacitor and do the same thing as before. So it's going to be the same equation except for this sort of innocuous factor of 2, right? So how does that help us? And the claim is that transmon made from this type of ingredients has the same insensitivity to this offset charge. However, it will have large and tunable anharmonicity. So let me explain that. And it can be seen from this simple diagram. So cosine 2 phi is here, right? And instead of a single well, as we had in transmon, we now have 2 wells. Now at low energy, they will be roughly harmonic near the bottom. So the energy levels near the bottom will be roughly those of harmonic oscillator in the transmon limit, right? If we just had a single valley, then that would be it. But now we have 2 valleys, and we have 2 sets of nearly harmonic levels. And you can see where this goes. If I plot a wave function of this ground state, there will be some overlap because these wave functions have some spatial extent in this phase, and therefore these 2 levels will actually be hybridizing, right? And this is exactly what happens. So the actual energy levels after this hybridization will look something like this. Okay, and that will happen with all of these levels. And so you can see right away that this no longer is harmonic, right? Because I start with two sets of harmonic equally spaced levels, but I weakly hybridize them. So there's another energy scale in the game, which is this hybridization, and this spectrum can be now very unharmonic. Okay? So all I have to now do is actually solve carefully this equation and show that there's this insensitivity to offset charge, but I can also have unharmonicity. And so that's what we've done, and actually my student Rishi was responsible for this calculation. Excuse me. So I told you that actual transmon, instead of one Josephson junction, actually uses two of them, and I will now explain why that is so. Basically, the reason is this: when you fabricate a single Josephson junction, you can't really, I mean, by fabrication, you can to some degree control its energy because it's proportional to the area, for instance. But this will vary from one junction to another, right? So the way, if you want to have really specific value of your Josephson junction energy, the way you do that is this trick where you put two junctions in parallel and then put flux, a magnetic flux in it through some nearby wire that produces magnetic field. And it turns out those two act as a single Josephson junction with junction energy that is tunable by this flux. And it's a simple calculation which I will not reproduce here, but you can find it on page 2 of any book on quantum computing. So that's exactly what we do here. Instead of that very simple design with just one D-wave flake on top of S-wave substrate, this is a sort of more elaborate proposal where we have D-wave flake, there's on S-wave substrate, and there's another superconductor on top, such that precisely we have these multiple Josephson junctions. In this case, we have 3. 2 of them are these red junctions between D and S, and one of them is just SS Josephson junction. And the reason for this construction is such that we can put some magnetic flux through that loop and control the Josephson energy. In the case of this D-wave construction, it gives us additional term here in the transmon equation. So these first 2 terms, they were there originally, and what this additional structure gives us is additional term here, which has cosine phi structure minus some external flux that we can tune by hand. Okay, and so this design is similar to what is being used for conventional transmons. This is a kind of more realistic variant of what people would use. So what we're solving, and what Rishi has solved, and I will show you the result of, is this particular equation where this extra term here can be controlled by the amount of flux that we put in through that hole. Okay, and yeah. So again, numerical solution of this equation corresponding to this more, whoa, okay. Something happened. So here's some figures that you should compare to the original transmon figures that I showed you. What I'm showing here is dependence of these energy levels of this Schrödinger equation obtained numerically as a function of this offset potential that is fluctuating uncontrollably. And these are various cases depending on this external flux. So this is external flux 0, external flux pi over 4, and pi over 2. And I don't want to belabor this too much, but you can see that in many of these panels, we have very flat energy levels, which is what we want. We want the energy levels to be insensitive to this offset charge. However, we have lots of unharmonicity, right? So for instance, here in this graph, there's huge unharmonicity. There is unharmonicity. Here, we can get unharmonicity that is positive or negative, meaning this level is much larger than this level, or we can get the opposite situation where this difference is much smaller, and that has some implications for details, how you operate these qubits, and people in the business are actually interested in negative unharmonicity, which is hard to get in conventional transmon. So with this design, we can get all of this essentially for free. Okay, so here's a kind of summary plot. And what it shows is two things. The top one is the flatness indicator. The darker, the more flat these are. So dark blue corresponds to very flat bands, and this is in the space of this external flux and the ratio EJ over EC. And this is the unharmonicity indicator. And again, blue is negative unharmonicity and red is positive. So you want to be somewhere in this range where the flatness is very large and unharmonicity is negative. And you see that there's lots of space where you can tune this kind of qubit to have these desirable properties. Okay, so when I first time gave this talk, somebody asked this question, so why am I thinking of SD junction? Why can we use this twisted DD junction to make this Dimon qubit? And the answer is, in principle, yes. And they already exist. And I showed you some experiments on these DD junctions. However, here's the problem. So somebody already picked up on this yesterday. So in this kind of design, where you have two D-wave flakes, the overlap region typically will be quite small, right? So this is where you have a fully gapped superconductor that has all the desirable properties. But then it's connected to these large flakes that are just pure D-wave superconductors. And they have all these low-lying excitations, which, again, you don't want to have anywhere near your qubit if you can help it. So that's why the design that we considered, this basic design, actually is such that we minimize the amount of D-wave superconductor, and our substrate is fully gapped S-wave superconductor. And in that situation, you shouldn't have these low-lying excitations. So there's a subtle question. So this was the hardest part of the project that we had to solve, and this is my last transparency, so I'm almost done. So at the mean field level, when you couple this D-wave superconductor to an S-wave superconductor, the result is this D plus IS, which is fully gapped. However, here's a kind of caveat. In order for this to function as a useful qubit, you need to allow the relative phase to quantum fluctuate. Okay, so you basically quantum fluctuate between D plus IS and D minus IS. In the process, you go through zero phase difference. And the intriguing question was, does this remain gapped, this system, in the presence of this fluctuating phase? And my colleague, Drew Potter, actually nicely solved that problem. And it turns out the answer is yes. And it turns out the answer is, in the transmon regime, the gap is slightly suppressed from the mean field value, but still large. It's suppressed by maybe 5 to 10%. But you can solve this problem. And this was the hardest part, which I will not really go into here because it involves some fairly serious calculation. So, okay, here's my summary slide. And I think I'm pretty much at the end of my line, so I will stop here. And thank you for your attention.
So basically, if I'm understanding correctly, by having this extra external flux, you're able to split all of the harmonic levels and stuff. So you mentioned before that in the cuprates, there's always a slight orthorhomicity. And so does this also provide another scale for extra?
Yes. OK, that's a very perceptive question. And let me just go here. Yes. So Yeah, at the beginning I said there was slight orthorhombicity which permits a small cosine phi term, right? So indeed, this design, there's a contribution. If you have orthorhombic material, there would be a contribution to this term from there. And the important function of this whole more complicated design is that you can control that contribution by actually inserting this flux and having two junctions instead of one. So that's a kind of more subtle way of reasoning, right?
So yeah, I suppose because there's the external flux, it's kind of irrelevant. That's what you're saying.
It's folded into this term, basically, right? So you can, if that term naturally would be too large, you can compensate and make it smaller. If it's too small, you can increase it through controlling that flux. So you can put it exactly where you want it in that sense.
For the question from C yesterday, like how large is the Joseph's energy here in the two-side junction to make it like predicate useful?
Okay. So yeah, so we made we tried to make a reliable estimate for the size of the Josephson energy, and it's not easy to do because, well, let me just say this. Sorry, let me go to my last slide. So this kind of simple structure is not really that well studied experimentally, right? So people have actually studied these type of SD junctions back in 1990s when they wanted to see whether cuprates are S-wave or D-wave superconductors. And they all uniformly concluded cuprates are S-wave because they didn't see anything unusual about these junctions. Now we know that they probably had a very dirty interfaces. So what I'm talking to two different groups. One is Philip Kim and there's another group. I'm trying to talk them into actually manufacturing these using these modern techniques and characterizing this type of junction so that we know what are their parameters, for instance. The good thing about this qubit is that, or when you want this for a qubit, is that the material parameters don't matter too much because this Josephson energy actually scales with the area of the junction, right? So if the Josephson energy per unit area is very small, you can just compensate for it by making a bigger junction, right? And yeah, we don't know the exact numbers, but one can compensate for this by geometry.
Maybe a quick follow-up. On the other hand, what's the desirable energy scale for this, say compared to noise and things like that?
Okay. So in typical transmons that are made universally from aluminum, the typical energy scales are quoted in gigahertz, and they are in single digits gigahertz because that's the frequency that it is convenient to operate. You can control, you can make pulses, and so on. Gigahertz, that corresponds to some small fraction of a Kelvin. Yeah. So kind of very crude estimates suggested that sub-micron size junction like this would have roughly that energy scale. But I would not bet my house on that because experiments still need to be done.
I have a question about the DD versus SD. So you explained the intuition for what happens with the DD junction with the degeneracy of the two values and how they hybridize.
Mm-hmm.
But for the SD configuration that you actually consider that's the same intuition applied, or is there something else that's going on?
Okay. So that what I explained was for this cosine 2 phi potential, and that would apply equally well for DD junction at exactly 45 degrees. You would have that cosine 2 phi, and for SD junction, it should apply for any angle because that's independent of the angle. So that's the same argument.
I have a question about the Majorana zero modes.
Mm-hmm.
And how, so my thought is okay, the logical qubit would be encoded in
if you have like some plate, that there would be like a Majorana zero node along the edge and around the vortex, or not? Is that like the
Okay, yeah. So
and then how would the braiding work,
yeah.
I guess?
Okay. So the high-level idea is that you need 2 Majorana modes to encode a qubit. That's the minimum number, because 2 Majorana modes form a shared complex fermion that can be empty or occupied, and you want to use those states as your 0 and 1. So what you would do in this case, presumably, you would use 2 vortices that are far away from any edges that have 2 Majorana modes, and that would encode your logical qubit. And then you would have additional pairs of vortices that would encode more and more qubits. And in principle, you could now, so you imagine you have some array of vortices at the beginning, and then you would affect operations on them by braiding them one across one another. That's the general idea. How exactly you would grab vortex and move it around, that's an unsolved problem, but that's the general idea.
Okay, so you can do this all within one superconducting plate.
Yes. Yeah, that's the idea. So in a sense, your quantum state is encoded in these collective degrees of freedom. And the reason why this is supposed to be robust against decoherence is that they are encoded non-locally, right? That if you just look at a single vortex, you cannot read any of that information. It's encoded non-locally in all the vortices collectively.